It's not an exaggeration to say that our nation's global competitiveness depends on how well we prepare our students in STEM fields. And that's why this conference is so important. Right now, we're lagging behind. As I travel around our state, I hear from schools, businesses, and communities that high-tech jobs are going unfilled because people don't have the skills to fill them. And in Minnesota alone, we're going to have to fill more than 180,000 STEM jobs by 2018. Encouraging young people to pursue careers in STEM fields is one critical step we can take to making sure that we can fill those jobs and keep our state and our nation competitive in the 21st century. And STEM isn't just about being economically competitive now and in the future. Having a solid knowledge of STEM fields is also just a part of what it means to be a well-rounded person and a well-informed citizen in the 21st century. STEM education is a top priority for me as a senator. As a member of the Senate Education Committee, I've been working to make sure that there is funding for STEM education and better training for STEM teachers. I've got a bill called the STEM Master Teachers Corps Act that will reward the best STEM teachers we have and give them the opportunity to serve as mentors to other STEM teachers. For the students here today, this summit is an excellent opportunity for you to learn about the variety of exciting and challenging career options open to you when you get a STEM education. Take advantage of this opportunity and talk to the companies and universities represented here today. Good luck and enjoy the summit, and thank you.
We will be meeting a lot of students pursuing careers in the STEM fields. And the number of jobs will be wide open for those students who prepare themselves. And this program is about helping you to prepare yourself for the future and for the future jobs. We're delighted that you're here today, and we want you to find this day a very rewarding, enjoyable one. And we want you to get information, and we want you to have a productive experience with the highly interactive, hands-on exhibits, and hope that that will encourage and motivate you to pursue a career in the STEM fields. I want to thank the companies and the institutions that are here, and also the support of the admissions staff, and also the Atwood Center has helped, and also the many companies that are here today. So let's give them all a round of applause.
Nitrogen is a monoatomic, single nitrogen, or diatomic fat. Monoatomic or diatomic? Diatomic, it's like O2. So, we have this liquid nitrogen, and what is in here? Oxygen. One guy says oxygen, one guy says air. Who's right?
Isn't it hydrogen? Oxygen would be air.
It is air. So a little oxygen and a lot more nitrogen. So if I take this guy, filled with nitrogen and oxygen, pour my liquid over it. Did you? Yeah. So you thought it would expand or contract?
Expand.
You thought it would expand. So how many people think it's expanding or contracting?
Contracting.
So is it getting warmer or colder?
Colder. That is the sound of a freezing balloon.
That is the sound of a freezing balloon, absolutely. So if I take my balloon, so it obviously shrunk, right?
Yeah.
So if I take it out, I'm going to let it warm up. And what's happening?
It's expanding.
So can you see that there's liquid in the bottom of the balloon?
Yeah.
And so that liquid in the bottom of the balloon is what?
Nitrogen.
But if it's liquid nitrogen, how did it get in the balloon?
Because it was in the air already.
So in the air already, so we took gas molecules of nitrogen and oxygen, turned them into liquid, and they turned back into gas. Just like that.
It was years ago that my father told me, he worked for DuPont Chemical Company, that Richard, chemistry is life. And that intrigued me. I think I was in about the 6th grade when he said that. I went on to get my doctorate in chemistry, and my work was sponsored by NASA. So I was intrigued by science from a long time ago. And I think some of you probably have that same kind of interest, and it's been sparked by someone in your life that said it's important. But I found it intriguing, and I found it always exciting when I did get into formal training, formal education in chemistry and so on. Again, welcome, and on behalf of the president, the faculty and staff and others, I'm glad to see you here. Now let me read the proclamation from Governor Dayton. From the state of Minnesota, proclamation. Whereas January 29, 2015 marks the 7th annual Science, Technology, Engineering, and Math, STEM, Summit at St. Cloud State University. And whereas the St. Cloud State University STEM Summit provides Minnesota's 7th through 12th grade students an opportunity to explore STEM topics with community members who have knowledge and expertise in STEM subjects. And whereas the St. Cloud State University STEM Summit highlights the importance and value of STEM education and connects Minnesota businesses, local government, teachers, parents, and higher education communities to STEM coursework, resources, and programs. And whereas the St. Cloud State University STEM Summit provides students with a better understanding of STEM, education requirements and opportunities, highlights in pursuing and in promising opportunities in STEM careers, which STEM careers provide, and equips students to succeed in science, technology, engineering, and math. And whereas STEM fields are the future of the Minnesota workforce and the Minnesota's economic depends on a well-prepared pipeline of students with the education and skills necessary to keep businesses and industries competitive. And whereas maintaining a high-quality STEM workforce for Minnesota and the nation by promoting STEM competency is a state priority. The St. Cloud State University STEM Summit will inspire students and allow them to envision their future with career success in an increasing competitive global marketplace. Now, therefore, I, Mark Dayton, Governor of Minnesota, do hereby proclaim Tuesday, January 29, 2015, as STEM Summit Day in the state of Minnesota. In witness thereof, I hereto set my hand and cause the great seal of the state of Minnesota to be affixed to this document in this 12th day of January, Governor Mark Dayton. And this is what it looks like. We'll have this framed and put in a prominent place here. Welcome the rest of you, and have a good day.
In STEM education, we don't really measure student success by having someone who come to our college, graduate with GPA 4.0, and that's it. We are very much interested of having you, if you come to study here in STEM field, a successful career. If you graduate with your degree from here and you get a job, and after 2 years you wouldn't be capable of keeping up with the fast-moving world around us, which is very characteristic of STEM jobs, we would not be consider ourselves successful in educating you in STEM field. So it is very much for us, very much important for us to give you this experience through interaction with industries, through exposing you to real world problems that will make you adaptable when you graduate out of here. The other thing that is very important for us is to make sure to increase the diversity in STEM graduates. We need more women, we need more people from different backgrounds, because this is what the industry wants. They are not doing this because of fairness or political correctness. They do this because this is good for them. From an employer point of view, if I have all my employees from one group of population, they think the same, they make the same decision all the time, but if you have a diverse group of people, you will be thinking out of the box. The box will be much bigger, and most likely you will make decisions that will be much more effective and for the benefit of the employer. So we will.
Okay, there you go. Now turn it to the side.
It's like a helicopter.
Like a helicopter, that's exactly what it is. Now turn it to the other side. And you spin the other way. Why? Why does that happen? Well, basically, all you're trying to do is you're changing your rotation axis, so if you switch that over there, it's also trying to conserve itself as well. So otherwise, same thing with, a helicopter like you were saying. If you have a helicopter, how many propellers does it have? 2. One in the top and one on the back side? Yeah, exactly. So what happens is if that didn't have the back side on there, all it would do is, just like you were doing before, is you would just spin one direction. The other way, it allows it to correct itself and fly in a straight path. It's like steering.
STEM, science, technology, engineering, and math, these are the skills that our children need for the future jobs. If they want to be successful, they need to be in the STEM.
But did you know that here in Minnesota, about 20% of all jobs are STEM related? So this is making up a large portion of the work that we need in our state and the jobs that are offered. And they're the fastest growing job category in the state. Not all the jobs are in these unique fields that I just mentioned. A lot of great jobs exist in construction and engineering, and you can have a really great quality of life in those jobs that are very much STEM related. Did you also know that the average wage for a worker in Minnesota is about $50,000 per year? But if you have a job in STEM, that average jumps to about $85,000 per year. So that's a significant difference and is something to consider. There are some jobs, like in oil and gas extraction, you can make over $362,000 per year on average. So that's a lot of money in anyone's world.
Science, technology, engineering, and mathematics. And this is one of the major initiatives that I have here. I want them to feel like they're in college. I want to help prepare them for the future and where their livelihood will be. And this is where their livelihood will be, having STEM skills.
What's happening is our population in Minnesota is increasing, and the people moving to our state are much more diverse than what the state is used to. In fact, the 5 top most common birthplaces of people immigrating to Minnesota are Mexico, India, Thailand, and Laos. And most of those people from there are called Hmong, and Somalia. So these are people from all over the world, and our system is not really set up to meet their needs as it currently stands. So 18% of our state are people of color, and yet only 11% of people in STEM jobs are people of color. This is a big difference, and something that, as Dr. Ali mentioned, is something that needs to change, even if you look at it from a productivity standpoint. If we look at how students are performing on state tests, students of color are way behind their white peers as far as science and math goes. And these differences are large and they're growing. But we can't say it's because of lack of interest. We know that fourth grade students students of color are actually more interested in STEM activities than white students in fourth grade. And eighth grade students actually participate in out-of-school STEM-related activities at a higher rate than white students. I suggest that what we have is a problem of opportunity gaps. And not everyone in this state has the same opportunities. And that's really where these differences are coming from. They break along racial, ethnic, and socioeconomic lines. And what that means is students of color have less opportunities to explore STEM-related activities. And not just STEM-related activities, there are others. So what can we do about it as a state?
And they don't necessarily have to be engineers or anything like that, but they want to have problem-solving skills and all of that, mathematical skills, because that is where the jobs are going to be. And if they have a job, that's what kind of skill they're going to need to do the job. You see?
I mean that I believe that every student, every adult has something that they're passionate about, something that if discovered, they will immerse themselves in and try to learn anything and everything about that.
And I'm very multicultural because I believe all students should get these skills. And if you know, I have all kinds of all districts, Brooklyn Center, Elk River. Elk River is getting a lot of people of color now. Did you know that? And this guy, he brings so many students from Elk River. And Rogers too. They have moved from Minneapolis to Rogers and Elk River in these places. That's because they can get transportation to get to school.
There's a saying out there, most popularly attributed to the playwright George Bernard Shaw, that many of you may have heard, that says, "Those who can do, those who can't teach." I really disagree with this. And guess what? Charles Mayo, the founder of the Mayo Clinic in Rochester, Minnesota, did too. And he said, "The safest thing for a patient is to be in the hands of a man involved in teaching medicine. In order to be a teacher of medicine, the doctor must always be a student." In other words, in order for people to do well in their jobs, they must constantly be learning and, more importantly, constantly be teaching others. Because I bet if you took a science or math concept that you just learned in class and tried to teach a younger sibling or neighbor or maybe a teammate, you have to know that subject really, really well in order for them to learn it.
So in physics we study like that kind of motion. By itself it's not that interesting, but what we learn is that the time it takes to go over and back depends only on the length of the string and the strength of gravity. But notice this string is shorter than this one by a bit, shorter than this one by just a bit. The longest string, that's over here, so that's going to be the longest time to go over and back. We carefully selected these lengths so that the motion taken together is pleasing to your eye. It's like music to your eye. You ready?
Yeah.
Yeah.
Science.
Physics.
Physics.
So make sure you lead by example. Make sure all your friends really want what's best for you, and you really want what's best for them. That's really the true definition of friendship. I challenge you to inspire your friends to dream, inspire them to learn, and inspire them to become the best they can be. Become a leader yourself. So in conclusion, if you remember just two things from what I've said this morning, remember these. First, STEM pays off, both literally and figuratively. Literally in that you can make a lot of money and you can have a great quality of life in a STEM career. Figuratively in that you can do good for others. Second, believe in yourself and believe in others. You will make mistakes. Others will make mistakes, but know this. Success is how high you bounce when you hit the bottom.
Questions, please just let me know that everything is completely flexible and it's up to us what we see and talk about.
I'm the organizer. I do everything, every minute, everything from organizing who sits where, who has a table where, everything. Who contacts the teachers, all of that I do.
Okay. And it seems like the mission or the purpose here is just to get young people excited about STEM fields.
Yes, to get them excited about STEM fields so they'll know and about the many careers in STEM. And that's so important, you know, because if they want to be successful and make money, that's STEM.
What we're going to do is we're going to do science. And the great thing about science is that until you know the science behind what you see, it all looks like magic. So we're going to start out with an old magician's trick, but we're going to do it with a little bit of science. So keep an eye on Jeff.
All right, so I got a bottle of water. Notice I took a couple sips already. And I'm going to pour water into the top cup here. Try to put the lid back on.
Manual dexterity is not necessarily the high point.
I even had coffee this morning too. All right, so we got water in this cup. We do not have water in these two cups. All right, so remember I told you you guys have to participate in this one, right? I'm going to point at cups. You guys are going to yell all yes or no whether there's water in that cup, all right? So here we go.
Yes, no, no. Water is in the red cup. Remember that.
It wasn't quite yelling, but yeah, they have it right. All right, now you've seen the shell game with the magician, right? Where they put the soft balls and they move them around, they ding with their magic wand, and the balls never were supposed to be. Okay, now that can all be explained. Anything a magician does can be explained. They just don't because they make more money if you don't know what's going on. Us scientists, back to the speaker earlier, we make so much money, we're happy to tell you what's going on, okay? We want more of you to join the party. So, can I turn this cup over though? No, so what we got to do is we got to do it this way instead of the magician way, so we're going to do a little bit different. All right, I'm going to slide the cups. You guys are going to watch this cup. We'll stop a couple times. I'll point. You guys will yell, and we'll go from there. All right, you ready?
Yes,
say yes. Ready? Yes. All right, here we go. Watch the cups, watch the cups, watch the cups. Here we go. Here we go, here we go, here we go. Where are we going to stop? We'll stop right here.
No. Yes. No.
Ooh, the volume's even better, too. All right, here we go. Keep watching, keep watching. Sliding cups, sliding cups?
Yes.
No. No. Yes. How much time I have left?
Another 20 minutes.
All right. All right, we'll do it one more time because we got other stuff to do. All right, so one more time. Where should I stop it? We'll stop it right there. All right, water in this cup. No. Water in this cup. No. So therefore the water's got to be in this cup. All right, now, you guys are exactly right. The water is still in this cup, but what we did is we put some powder in beforehand called sodium polyacrylate. I'll come back to the camera guy. All right, and so what we did is we turned that free-flowing water, got grabbed onto this by the particles that were in there, the sodium polyacrylate, and kind of turned it into a chunk of Jell-O. You guys over there see it? Now, as we understand it, this was invented by a chemist at the Dow Chemical Company, okay? And I've read anywhere from it retains, 200 to 500 times its weight in water. And what's interesting is the particles, when they get wet, they stick together. So, the guy or gal that came up with this, discovered the properties, now has the same issue that we have at 3M, is that we get to do really great science, but ultimately we have to sell it. Okay, 3M's in the company in the business of making money. We do a lot of science, but ultimately we're in business to make money. They had to come up with a way to use this. It turns out this is actually the first place this was used is in disposable diapers. Okay, if you got relatives around that have a little one that are still in diapers, ask before you do it because the diapers are expensive. But if you tear it and shake it over a table or a counter, a little bit of powder will come on. Now there won't be this much in there, but the idea is you take the water away from the baby's skin. The baby's skin is healthier, and turns out that's a great big market. They can make lots of money there. We're starting to see it in potting soil and on seed coatings because the water that's in there is not chemically reacted in. It's what we say physically adsorbed on. It can come back out. So you put it in the ground with plants, get it wet, it'll stay there, it eventually comes back out, the plant can use it, so if you're going on vacation, you don't have to hire the neighbor kid to come over and water your plants, you can just let the water come back out of the crystals that are in there. Okay, the space saver bag or the vacuum storage bag, and the idea is it's basically a great big Ziploc bag. It comes with little clips to make sure it seals well. So the idea is that you take something like a pillow, put it inside the bag, seal it up with the handy dandy little tool I give you, and voila, now you have a pillow in a bag. Of course, this really doesn't do anything, and now you just have a pillow in the bag, right? It still looks exactly the same, but the idea is now you hook your vacuum cleaner up to this valve on the backside, hit the switch, start to take some air out of the bag. And what happens is by taking the air out of the bag, the air pressure around this now pushes on it, flattens it down, and so if we're putting it in the closet, you have a lot more space because now it's real flat.
It doesn't seem like it's a great way to take a nap, though, Jeff.
No, the key to this thing is this one-way valve here. It lets air go this way, doesn't let air go back in. Okay? Now, but yeah, like Mike says, not a great thing to take a nap on now, is it? Kind of looks like a pillow turkey. So, come afternoon time and you want to take your nap, the idea is you open the bag up, air comes back in, and the air goes back into the pillow, and the pillow reinflates. And so, for using it, it is now ready to take on our nap. Those of you that are in high school have taken chemistry probably know how much the air pushes on us. It actually pushes on us a lot. And it'd be really neat if we could somehow measure how much air is pushing on us. And so we kind of modified a bathroom scale. And normally you put this on the floor, you stand on it. Depending upon how much the springs move, they're calibrated, so the further the springs move, the bigger the number it puts up on there. But if we put the bag, or put the scale inside the bag, and we do the same thing and have the air push on both sides, well, that should squeeze on the spring, shouldn't it? Okay? So it seems like it's a logical experiment to try. All right, so this scale kind of is a little finicky. The spring-loaded one, the spring ones are a little easier, but we like digital. Now, we're in.
Okay.
All right, you gonna survey the group or you want me to?
All right, let me do a quick survey. All right, the scale reads from 0 to 300 pounds. So as Jeff pointed out, we're gonna take a little air out of the bag. We're gonna let the air pressure in the room press against the scale. It's gonna give us a reading. How many people think that it's gonna read between 0 and 50 pounds? Raise your hand. 50 to 100. Between 100 and 200 pounds. 200 to 300? More than 300. All right.
Look how many people weren't paying attention.
Okay, the scale goes from 0 to 300.
So what we're going to do is we're going to get this set up. We're going to get it to read 0. You're going to pull, hit the switch over there when I tell you. All right. All right, hit it. All right, so it's going to think, it's going to think, it's going to think. .6 pounds.
All right. Okay, 246. How many of you guessed between 200 and 300 pounds? Well, all right. Now, how many of you actually didn't guess that and you just put your hands up right now?
Say there's more hands up now than there was when we were asking for a
Okay. All right. You know, Jeff, I don't think that number is right. 246, that doesn't seem right to me.
Yeah, because it seems like we don't feel air.
No, if there was 246 pounds pressing against me, I mean, after all, look at this. That's like the size of my chest. If I had 246 pounds pressing against the side of my, against my chest, I would notice that. I don't think this is right.
Billy, you know what? You are right. It's not right. But it's too small.
Too small?
Yeah, it turns out this shop vac only can take out about 10% of the air pressure. So we really need to multiply that number by 10.
So 2,460 pounds against my chest?
Right. Kind of like a small car.
Yeah.
Now, if we parked a small car on Mike, do you think you would notice that? Who thinks we should try it? Raise your hand.
Hey. The last time we did this, it did not go well, and I complained for like 10 days.
Yeah, at least.
It seemed longer.
Yeah. All right, so that being the case, why aren't we crushed by air? Because, you know, we can do the measurement, figure out how many square inches this surface is here, and it turns out air at sea level pushes 14.7 pounds per square inch. I think I have a quarter in my pocket.
So it's like the size of a quarter.
Yeah, so if we take a quarter, that's, you know, roughly a square inch, even though it's round.
A round inch?
Yeah.
Okay.
All right. So right now, if I put that quarter on my hand, hold my hand out here, it turns out the air on top of my hand is pushing, you know, about 15 pounds just on the quarter. Okay, that's like a bowling ball, right? Can I get more than one quarter on my hand?
Yeah, actually, I've seen Jeff put a whole stack of quarters on his hand, but that's a different, that was a different environment. And
yeah, so anyway, let's say I can put 10 quarters on the surface of my hand, and I think I can do that. So that's 10 bowling balls, that's 150 pounds. So am I just really strong, or is there more to the story? You guys are old enough that you know that there's more
I
to the
bet
story.
it's magic.
No, science.
Science. All right.
We just do
So-
science.
So the science behind it, Jeff.
Well, there's air underneath my hand, right? And it turns out air pushes in all directions, so the air on top of my hand's pushing down almost 15 pounds per square inch. The air underneath is pushing up almost 15 pounds per square inch. Almost 15 minus almost 15 is 0.
All right, that was a lot easier than that engineering professor coming up here, right?
All right, so that's why we don't notice air pressure. We have air inside of us. We're balanced. As soon as the air pressure is balanced, everything is fine. Our ears are real good pressure monitors. If you go up in a really fast elevator, really long elevator, go up and down in an airplane, big hills, we feel something in our ears, right? And as the pressure inside our ear and outside our ear varies, our eardrums flex a little bit. We don't like that. We can feel it. We need to swallow. We'll balance it on both sides. It straightens back out. Everybody's happy. And but it turns out our ears tend to be really, really good measurers of air pressure.
When air pressure is balanced, both inside an object and outside of an object, we don't notice what's going on. But when there's a difference between the air pressure inside and the air pressure outside, that's when we start to see some effects. So one thing I've always wanted to do is blow up a balloon in a bottle. Now, how many of you think that's really cool?
How many of you tried to do it before?
How many of you succeeded? All right.
And is there anything in the globe besides a balloon? Air, right? And all that pressure we just talked about is still inside there because it's open to the room air, so it's in there. So if I cover up the hole, you think Mike's going to be able to blow the balloon up very far? No. All right.
All right. Stop me
Prove them wrong, Mike.
Stop me when I get to husky red. All right.
All right. No, a little more. All right, that's about it.
Oh.
All right.
Well, I felt that air pressure equalized, and one of my eardrums actually blew out. But, yeah.
All right. So, with the air still in here, air is matter. By definition, as mass takes up space, Mike's got to blow against that pressure, so he can only get it so big. If we hooked up a big high-pressure tank, we can maybe get it to look bigger inside there. But ultimately, the air pressure is going to keep it from being completely full. Now, I'm going to give it to him. Let him do it himself. Hopefully, he won't cover up the hole. Now, hang on. Now, do you think it'll work if we allow the air to come out? All right.
Okay.
Now, again, we got a problem though. Once you fill it up, you can't pinch the end off.
All right.
It's on that glass thing.
So I have to keep blowing.
Yeah, or you're gonna have to hold it or something,
okay.
probably.
All
Anyway,
right.
so go ahead. Let's give it a try here. All right. So, allowing the air to come out, now the balloon can push the air out the back. So Mike's able to fill it up. You can make it fill up the whole thing. Keep going.
I'm getting a little tired. I gotta take a break.
Oh,
Okay.
here, give it to
So,
me
yeah.
then for
All
a
right.
second.
Hold that for a minute.
Wait
I
a
got
minute.
it.
Wait a minute.
Well, I'll keep blowing on it to hold that balloon up
All right.
in just a minute. All right.
Well, why isn't it? We stretched that balloon. The balloon doesn't like to be stretched. Why is it still open? Oh, I know.
Remember this? The one-way valve. So obviously, I snuck a one-way valve in there, right?
Or not.
Oh, wait a minute. What happened to the one-way valve?
It's not in there. I can see right in it. The inside of the balloon looks like the outside, except it's curved the other way.
Okay, but we had air pressure that's inside the balloon that holds the balloon out, and then there's the force of the rubber that's trying to squeeze that air pressure out. We've got air pressure, it's the same air pressure on the outside of the balloon pushing against it.
Oh, I know. We put tape in here.
Sticky on the inside. That's not it. They
Well, we make lots of tape.
yeah, but then we have to clean it out, and people get all uppity when they have to clean this thing out.
All right.
So the real key to that is the air pressure in the room is pushing against the glass globe. Now, how many of you were doing careful observations, which is the first step of science? How many of you saw me when I was inflating that balloon, I put my finger inside and poked the balloon? That is the magic behind the science, all right? What I was doing was I was deforming the balloon so that the air that was trapped between the balloon and the glass on the inside of the globe, so a lot of that air could sneak out. It wouldn't be trapped between the balloon and the glass. So now what do we have? We've got air pressure inside the balloon, that's inflating the balloon, but very little air between the balloon and the glass, so we don't have that balanced air pressure pushing against the balloon. So the air pressure inside the balloon is enough to overcome the force of the rubber that's wanting that balloon to shrink back and let that out. So we can equalize the air pressure by letting a little air in between the glass and the balloon, and then the balloon should collapse. And it does.
All right, so if we have more pressure on that side than this side, the balloon will stay inflated, is what you're saying.
That's exactly right.
Or if we really changed it, we could maybe even make the balloon get bigger. I bet you I can do it from this side.
How many think Jeff can inflate the balloon from the back side of the balloon, from the outside? All right, we got a few people. A lot of doubters, though. All right, now, is Jeff going to be able to keep that balloon inflated? Is he going to do the same thing like I did and be able to take his mouth off of the balloon? No, because there's no way he can get that air outside. He can't stick his tongue in there and force the balloon. We don't want to see that, all right? So Jeff has got to do this. Now, there is one way to equalize that, and here we go. All right, that's the Pillsbury Doughboy demonstration.
Hey, wait a minute. Who thinks pressure will go up when we move air? Who thinks pressure will go down when we move air? Still didn't get everybody to vote, but it was better.
Yeah.
All right, but based on how I said that, it turns out that both are correct, because in the direction we move the air, if we switch our shop back to blow air, we can see that the pressure goes up in the direction that we're moving the air. It turns out all the way around that stream of air, though, pressure actually goes down. Okay, Daniel Bernoulli discovered this a couple hundred years ago. It's now called the Bernoulli principle. It's basically what allows an airplane to get lift to get off the ground to fly an airplane.
So you're saying that I could actually take this piece of paper, and we saw that when I blew, that when Jeff used the vacuum to blow on it, the paper moved. Okay, that's obvious. But now you're saying that if I don't blow on the paper, I can get that paper to move?
If you don't blow on the paper.
If I don't blow on the paper.
Are you going to blow somewhere else, though?
Yeah, I have to blow somewhere else, right?
Okay. All right. So yeah, so now look, if he blows over the top of the paper, you kind of would think the paper should go down. But because he gets that stream of air going over the top, there's less pressure in that area, and so the air pressure is still underneath, and so it actually is able to lift the paper up. And you'll notice that the way he's holding that paper kind of looks exactly like the front end of an airfoil on the wing of an airplane. And the idea is that if the air hits this at the same time, the air that goes over the top of the wing's got to go faster than the air that goes under the wing for him to meet at the backside again. And so that speed difference on the top versus the bottom is what provides the lift to get an airplane to go up off the ground. Now, there's a lot more to flying than just speed. Okay, so don't think you can make a wing and ride your bike down a big hill or something to go flying. You
could do this once, but the key point to all flight is takeoff and landing. And if you don't master both of those, then things go bad.
That's right. Takeoffs are optional, but landings are mandatory, right?
That's correct.
Yeah. All right.
All right.
All right, so we can show this airplane idea by taking a ball, putting it in our stream of air here, and we can kind of get it to hover. It looks kind of cool. All right, so Mike usually says, wait a minute, Jeff, you got a force going up in the air and you got gravity pulling down. The ball just gets in the spot where those two forces are the same, and that's exactly true. But we're going to do it again, but watch that the ball wiggles back and forth more than it goes up and down. It'll go up and down until it finds the spot, but then it starts to wiggle this way because it is trying to fall out of there. But again, because we have this stream of air going through the middle, we got less pressure. The room air, literally, when it starts to fall out, shoves it back in, keeps it in the center. Okay, see how it's wiggling back and forth? It literally is trying to fall off. Now, I'm going to have Mike turn the air off here. All right, now that looked really amazing, right? But unless this ball flicks a little bit right at the end and hits the edge here, as long as there's air moving, there's going to be more pressure on the outside. It should sit right in there. All right, now I got a red ball that's basically the same size. You tell me if this one's lighter or heavier than the green one. Oh, there we go. It's sitting a lot higher. Therefore, you think that ball's heavier or lighter? Lighter, very good. Oop, I lost it, huh?
Yeah.
Give me the big one then.
All right, here we go.
That one's easier for me to watch. All right, now, it turns out the beach ball is real easy because we got big diameter on it, big circumference, and it's very light. Notice that the ball, well, we got a little bit of an air vent over there, but notice that the ball doesn't spin a whole lot. Okay, because the amount of air going around the ball is very, very balanced, so it doesn't spin very much. But now we can actually take this, and this is a highly trained beach ball. We've had it for a lot of years.
So
I can actually
gravity
make it go over by Mike over here.
So we've got gravity coming straight down, but the force of the air is off in this direction. So it's no longer just balancing the gravity.
Now it turns out, hopefully Mike won't fall off the stage, but we eventually can get the ball out far enough that gravity wins the battle. Man, look at that thing, it doesn't spin at all.
We don't have much time, Jeff.
All right, there we go. Point well taken.
Yeah.
So anyway, so we can actually now tip that, so we don't have those forces acting opposite each other anymore. But again, because it's that pressure difference, we now can still hold that ball up by the air moving around it. So what we have back here is we have a trash can that's got a hole in the bottom. Okay, and then we put a rubber cover on it. So what we can do with this now, if I hold this the right way, there's a handle on it somewhere. There it is. Okay, if I hold the handle, okay, did you feel that? Yeah. We actually can now start to throw little bursts of air. So Mike's got his fire on in there. All right, only 2 times. And that was all without even seeing where the air was going.
Yeah, the real problem with doing air experiments is you can't see the air. So this was actually, the fact that Jeff got this on 2 shots is really, yeah.
Pure luck.
Pure luck, but really cool. Now, sometimes it'd be really nice to be able to see the air. So if there was only something we could put in the air to be able to see it.
All right, so let's take it over here and now. Sorry. All right, still got a light?
Yep.
Let's do it again. All right, now notice when this goes by, people in the back probably aren't going to be able to see it real great, but it turns out that ring that comes out of there actually has thickness to it, okay? It's like a donut, okay? Because we get a little turbulence going, kind of a little bit of the Bernoulli thing happening, and so it turns out you end up with that toroid of air that stays together, you notice, a long time. In fact, we lose the fog before we actually lose the air. I do like that one. All right, so we got a square in. We're going to give it a bounce here. You think we're going to get a square?
Yep.
Oh, it turns out we're learning a little bit about energy. Okay? First of all, a circle's a low energy state, so it's going to want to try to go to a low energy state. For it to keep a corner, we've got to fight against entropy, and thermodynamics doesn't want to fight against entropy on the surface of the Earth here at the temperatures we live. Again, most of the air is coming out of the center. It's a little bit turbulent. If you look, you can see that it kind of waggles a little bit. Is that a word?
Yes, waggle is a word, an official scientific term.
And then, but eventually, once it gets far enough away, it kind of all gets put back together again like it should. And with that, our time is up. Thank you for your attention. Enjoy the rest of the day.
Thank you.
Dr. Karen Williams is in her speech 16th year at St. Cloud State University. She has been Associate Dean and Interim Dean in the College of Liberal Arts. She has helped countless students and colleagues who valued her wisdom and guidance through the years. She is a consummate helper of students to do their best in college and beyond. That's more important. She worked in Vanderbilt University before coming to St. Cloud State. She is instrumental in starting and nurturing many initiatives, including this summit you are attending, which has grown in leaps and bounds. Thanks to her commitment and initiative, SCSU became one of the first universities to participate in the Science Festival in Washington, D.C. with great honor and delight. I am happy to present this award of recognition for all her passion to bring STEM and life lessons to many students and faculty alike. Thank you, Karen.